Good day, students, and welcome to Lecture 4 of the Allen 2016A Electronics 1 course. I'm your lecturer for today, Mohammed Dango, and we'll be covering multiple diode circuits and AC equivalent circuit. Looking at today's lecture, we're going to be going through diode models, diode circuits, multiple diode circuits. We're then going to derive a linear AC model and perform some circuit analysis. All of this work can be found in your textbook in Chapter 2 and Chapter 1, and you know the rules. Anything said or done in this lecture can and may be used as a question to test you in your examination. So starting off with a bit of a recap, if you'd remember from our previous lecture, we can model a diode using three different kinds of models, depending on whether it's reverse biased or forward biased. The first model being the ideal model, and in this model, if a diode is reverse biased, we simply replace it in a circuit with an open switch. If the diode is forward biased, then ideally it looks like a closed switch. If we were to model our diode using the constant drop model, then we simply model it when reverse biased as an open switch in series with a source, which has the potential of the diode on voltage. And if the diode is forward biased using the constant drop method, we simply model our diode as a source or a battery with a voltage equal to the diode on voltage. And finally, you'd remember the piecewise linear model, which we derived from the characteristic curve using linear approximations. We can model a diode using the piecewise linear model when it's reverse biased as an open switch in series with a source or battery in series with a resistor, which represents the diode's resistance. And similarly, when we forward bias it, our switch becomes a closed switch in series with a source or battery, which is represented by the diode on voltage, in series with some small diode resistance. Now that you're back on track with diode models, let's look at an example. So here we have a 5-volt source in series with a diode, in series with a 1K resistor, and we're trying to figure out what is this output voltage over here. So we start off by replacing our diode with the piecewise linear model. So we have a source which is 0.7 volts because this is a silicon diode, and we have it in series with some diode resistance, which is 1 ohm because that is a very small resistance. We then label our circuit so that we have our diode current, and we put a nice little loop here so that we can perform the KVL analysis. Now students, this is a very simple example, so I expect you guys to be able to rush through this. If we do our KVL, this is the equation that we arrive at. From this equation, we can calculate our diode current. From our current, we are able then to calculate the output voltage by multiplying the current by the resistor. And just for fun, we can calculate the power dissipated across the diode by simply taking the diode voltage multiplied by the diode current. Moving on, if we were to reverse bias that very same circuit by simply flipping around this 5-volt source, you see that the negative terminal is now connected to the anode of the diode, whereas the positive terminal is coming to the cathode. So that is a reverse bias diode, and we replace it with an open switch in series with a source which is equal to the diode on resistance in series with that diode small resistance, and we have our 1K resistor. We label our diode current ID. So we have our KVL again, but since we have an open circuit over here, we know that no current is going to flow through the circuit. So very simply put, our diode current is 0 milliamps. Now then, we're going to work with another example, but this time we're going to be using the constant drop model. Now students, the reason for this is the diode resistance RD. When you calculate the Thevenin equivalent resistance at that point, you will find that it is much greater than that actual diode resistance. And it's for that reason that when we do diode circuit analysis, that we prefer to use the constant drop model, because that diode resistance is so small that it's negligible. So here we are, an example with the constant drop model. We have a 5-volt source in series with a 4K resistor, in series with our diode, and we have a 3K resistor and another minus 3-volt source connected at this point, and an output voltage. Now students, when you see circuits like this, either in your exam, your test, or your textbook, you might find it difficult to wrap your head around what it looks like, to vision exactly what's going on. I know that I personally struggle with that, so my thing is I just simply redraw the circuit. So looking at this circuit, if we were to redraw it, this is much easier for me to analysis. We have our 5-volt source, 4K resistor. We've now replaced our diode with the constant drop model, which is a 0.7 volt source. And we have our 3-volt source. Remember, this was minus 3 volts, so I simply spun it around. And now, students, if I were to perform the KVL, for me, this analysis is much more easier than the circuit on the top here. I can see what's going on and get my KVL equation. Very easy at this point. KVL equation gives us this. From that, we can look at our V1 plus V2, which is the voltages across our two resistors over here. We then can calculate our diode current. From there, going back to V1 and V2, we can calculate the voltage across those two resistors. And then finally, because we know the voltage across the resistor V2 over here, we know that the output voltage can be calculated by just taking this minus 3 volt source. So the difference between the output voltage and this minus 3 volt source is the volt drop across this resistor. That's how we get this equation. And voila, we can calculate the output voltage. Again, students, this should be a very easy circuit for you to analyze. I think the only difficult part you might run into is perhaps visualizing what's happening in this circuit and then having to redraw the circuit. The best way to get experience with these type of examples is just to do as many as you can. Perfect practice makes perfect. Now moving on, we're now going to look at multiple diode circuits, and we're going to kick things off with some series diodes. So looking at the circuit, we have two diodes in series, a silicon diode and a germanium diode. Now students, if you'll remember, the on voltage for a silicon diode is about 0.7 volts, but for a germanium diode, it's somewhere about 0.3 volts. So when we redraw the circuit using the constant drop model, this is the equivalent circuit that we arrive at. We have a 0.7 volt source, which represents our silicon diode, and a 0.3 volt source, which represents our germanium diode. Again, a KVL loop is what we're going to use to analyze this. So from our KVL loop, we are able to get this equation. I've already simplified it quite a bit to make the diode current the subject of the equation. Students, if you cannot follow, I suggest you perform this KVL analysis on your own. I'm sure you've got your slides in front of you with your pen and paper. Perform the KVL analysis and work it out till you get the equation of this. From that, we can actually calculate our output voltage using our current multiplied by our resistance. We get 4 volts. And now students, just for fun, if we were to look at the power in the circuit, this equation here is to calculate the total power in the circuit. So the total power in the circuit is going to be delivered by this 5 volt source over here, because that is our supply to the circuit. And since it's a 5 volt source, and we know what the current is that is going through the circuit, we know that power is equal to voltage multiplied by current. We have a total of 20 milliwatts that our source is providing to our circuit. Now let's see how that 20 milliwatts is distributed across the 3 circuit components. For our silicon diode, we simply do IDVD. We know it's got 2.8 milliwatts. For our germanium diode, again, simply current multiplied by voltage, 1.2 milliwatts. And finally, for our resistor, we change things up and we simply have our I squared R equation for power, and we get 16 milliwatts. If we are to sum these 3 powers up, 16 plus 1.2 plus 2.8, basic arithmetic, we arrive at 20 milliwatts. So that is the power in the circuit, so that you guys know what's going on. Moving on to parallel diode circuit, students. Here we have 2 silicon diodes in parallel with a 3 volt source that is in series with a 250 ohm resistor. And what we're trying to do with the circuit is calculate this output voltage as well as the current that's going through each of these diodes. So let's redraw our circuit, replacing our diodes with the constant drop model. So we have two 0.7 volt sources that we've replaced them with. Now students, what you need to note with this slide and this analysis is that this output voltage is one big node that is connected to the positive terminals of these diodes, or rather to the anodes of these diodes. Now, I'm sure you guys have remembered nodes and supernodes from circuits 1. Well, remember that stuff and take a look at this. So because this output voltage node is the same node connected to the anodes of our diodes, it's easy for us to note that this output voltage is equal to 0.7 volts, as we have written it over there. So now that we have the output voltage at 0.7 volts, it's very easy for us to calculate this current I that's going through the resistor. Simple Ohm's law, 3 volts at this side, 0.7 volts at this side, divided by the 250 ohms resistor, we get 9.2 milliamps as the current. Now you're probably wondering, where does the current end up going after that? Well, students, because we have two identical diodes, the current's simply going to split evenly between the two of them in our parallel circuit. So ID1 is equal to ID2 is equal to 4.6 milliamps. Now what if we have a parallel diode circuit that has two different types of diodes? Take this one for example. So here we have a silicon diode, but we have it in parallel with a germanium diode. And we know that the volt drop or on voltage of these two diodes are very different. So we replace our circuit with the equivalent model, and we have our 0.7 volt source here and our 0.3 volt source over here. So students, it's quite important to note that this 3 volt source does not instantly come to 3 volts. There's a small transient that takes place where it has to rise from 0 to 3 volts first. Now in that period of time, as the source is rising from 0 to 3 volts, it's first going to reach 0.3 volts before it reaches 0.7 volts. And once it reaches 0.3 volts, which is the diode on voltage for our germanium diode, what we're going to see happen is our germanium diode is going to turn on. So our germanium diode is going to turn on at 0.3 volts. But if our germanium diode turns on at 0.3 volts, what's going to happen to our silicon diode? Well, students, the silicon diode isn't actually going to turn on. And that's what happens in the circuit that you see here. So this 0.7 volts that we've replaced our diode here should actually be replaced with an open circuit, because we know that the circuit will actually never turn on. So once our germanium diode turns on, and it turns on first, then it's easy for us to calculate our output voltage over here. So simply our output voltage is the 3 volts which is being supplied to the circuit minus the 0.3 volts which is our germanium diode over there, and that gives us 2.7 volts that ends up over here as our diode on voltage. Because we have a resistor in the circuit, we know that it's going to draw some current I, and to calculate that current I, we simply take our voltage, which is our output voltage, 2.7 volts, divided by that resistor 250 ohms to end up at 10.8 milliamps. So, just to recap, students, this 3 volt source does not instantly arrive at 3 volts. When you connect the source to the circuit, there's a small transient where this voltage rises from 0 to 3 volts. And as it rises from 0 to 3 volts, it obviously hits 3 volts first, and at that point the germanium diode switches on and takes over the circuit. It never does get to 0.7 volts, so it does not switch on the silicon diode. So now, students, let's look at a bit more of a complex circuit for multiple diode circuits. You're familiar now with series diode circuits and parallel diode circuits, but what happens when they throw something at you like this? Well, my first thing to do is to redraw the circuit. As you can see, I can't make quite much sense of what it looks like here, So I simply redraw the circuit to something that is more manageable. Now students, this specific example of the circuit will not be covered in this lecture, so I encourage you to attend the lecture enrichment session so that we can go through this together. Now students, when you are analyzing multiple diode circuits that are complicated and complex like the one that we see over here, there are certain steps that you need to take in order to arrive at your solution. Now the first step that is taken is to assume the states of the diodes within the circuit. So if we look at a two-diode circuit, we know that the circuit have four possible states. The first being D1 and D2 both being on, so we'd replace them both by our constant drop voltage source. The second state being both D1 and D2 being off. In that event, we would replace both the diodes but with an open circuit. The third state being only D1 on with D2 off. So D1 will be replaced with a 0.6 volt source and D2 will be replaced with an open circuit. And the fourth state being D1 being off and D2 being on. So D1 will be replaced with an open circuit and D2 will be replaced with its source. So you can only analyze the circuit using one state at a time. So once you've made an assumption to select which state you'll be analyzing the circuit in, the next step is to go ahead and redraw your circuit. And when you redraw your circuit, you simply replace all your diodes with the model based on the assumption you made. And of course, you need to then label your circuit so that you have all the currents and all the voltages looking nice and neat for you to make sense of what's going on. Because that leads us to step 3, students, which is where you actually perform the circuit analysis. Now, when you go through the circuit analysis, you're going to arrive at certain diode and voltage equations or numbers. Now, when you have assumed that a diode is off and you analyze the circuit and find that the current going through the diode is equal to 0 and the voltage across the diode is less than or equal to the diode on voltage, your assumption has been correct. If you perform your circuit analysis and you assume that your diode is off, and you find out that the current that's going through your diode is greater than or equal to 0, and or the voltage across your diode is greater than the diode on voltage, then you know that the assumption that you made is incorrect. Students, if you're not with me at this point, don't worry. We're going to do an example to take you through this, and I think it will make things a lot clearer. But moving on, if you had assumed that your diode is on, then when you perform your circuit analysis and you find that the current through the diode is equal to 0, and the voltage across the diode is less than or equal to the diode on voltage, you know that your assumption is incorrect. If you assumed your diode is on and you performed your analysis only to find that the current through your diode is greater than or equal to 0 and or the voltage across the diode is greater than the diode on voltage, then your assumption is correct. You then move on to step 4, students, which is simply that if one of your assumptions was incorrect, you then have to restart all the way from step 1 with a new assumption on your circuit. You then have to redraw your circuit with the new assumptions, carry out the analysis, and check whether these hold true or false. So it's very important, students, that when you are analyzing multiple diode circuits, you have these equations at hand, so that when you perform your circuit analysis, you can see whether or not your assumption is correct or it is incorrect, and whether or not you have to go back to redo the analysis. So you're probably thinking that this is going to be quite a tedious task when analyzing multiple diode circuits, and you'd be correct. But students, my advice to you when dealing with circuits like this is to try to use some of your intuition to determine or assume what's going on within the circuit, so that the assumption that you make with your diode steps can be as close to what it should be. Now students, let's go through an example so that you can really understand what's going on with analyzing multiple diode circuits. So here we have a circuit, and the diodes in the circuit have piecewise linear parameters of a diode on voltage of 0.6 volts, a diode resistance of 0 resistance. Determine the output voltage V out and the diode currents ID1 and ID2 for the following input condition. VA is 10 volts and VB is 0 volts. So here, students, we have the circuit that was given to us, and because this is a difficult circuit for my head to figure out what's going on, I've redrawn it here so that I can see all the lines and exactly where everything is connected. And now I can go ahead and start with my analysis. So the first thing is we make our assumptions. Now remember, students, I said that in step 1, when making the assumption, you need to use some of your intuition here so that you can perhaps make an assumption that is as close to or correct. So if we know that our voltage VB is equal to 0, that's the voltage over here, it's a good assumption that perhaps this diode D2 is going to be off, because we know that in order for this diode to be on, it needs to have a positive voltage at the anode, which is greater than or equal to the diode on voltage of 0.6 volts. So if we are already starting off with a voltage of 0 volts at this point here, connected through a resistor to the diode, I think it's a good assumption that this diode's most probably going to be off. Now, whereas if we look at diode 1 and VA is given at 10 volts, as you can see here, the 10 volts is connected through the resistor to the anode of the diode. I think, students, it's a good assumption to think that this diode's probably going to be on. So let's do that. Diode 1 on and diode 2 off is our assumption. Step 2 is we redraw the circuit, and I've already done that. As you can see, I've done it for both circuits. So if you prefer analyzing circuits looking like this or like this, you have them both. So diode 1, because it is on, we leave it in place and we have a current ID1 going through it. Diode 2, because it is off, we replace it with an open circuit. The next thing, students, is to do step 3, which is the analysis. So looking at the analysis, I've cleaned up the circuit quite a bit. Because our diode 2 was an open circuit, we could have just removed that entire branch. As you can see, I've removed that entire branch, cleaned up the circuit, much easier to work with. We have a KVL loop now that we can perform. So according to KVL, 10 volts minus the voltage V1 across this resistor, minus the diode on voltage, which is 0.6 volts, minus the voltage across this resistor V3, all equals to 0. That's our KVL. So from our KVL, we simply rearrange this equation to make the diode current the subject. You replace V1 and V3 by Ohm's law. V is equal to IR, so that you can get ID1 as the subject of this equation. And you simply solve it to get 0.94 milliamps as this current ID1. And of course ID2, because this diode is off and it is an open circuit, that's going to be 0. We can then calculate our output voltage, which is simply the current 0.94 milliamps multiplied by this resistor here, and we get our output voltage at 8.93 volts. So now, students, we need to check. Remember, step 4, we need to check whether our assumptions were correct. So we assume that diode 1 was on. So because we assumed the diode 1 was on, for our assumption to be valid, the green tick, the current needs to be greater than or equal to 0. Aha, 0.94 milliamps. Last time I checked, that is greater than 0. We don't even have to bother with the diode voltage because it is an and or. So we've already got this. We know that our assumption is correct. And that, students, is how we go about solving multiple diode circuits. Now you're probably wondering, what if I went and made the wrong assumption? So let's see what happens if we go ahead and do that. So for some reason you assume that diode 1 is off and diode 2 is on. So let's redraw our circuit. Diode 1 is an open circuit. Diode 2 stays in place. It has its 0.6 volt drop across it. And we now can proceed with the analysis in step 3. So with step 3's analysis, we find that ID2 is equal to 0 because the voltage source that was here is 0. So that means we actually have no source in the circuit, which means no current ID2 is actually going to start flowing anywhere. So ID2 is equal to 0. And if we look at the assumptions, because we assume the diode is on, if the diode current is equal to 0, then our assumption is incorrect. And that is what we see here. Also, if the diode voltage VD is less than or equal to VD on, which it is because this diode voltage over here is 0 volts, we know that this assumption that we made is incorrect. And unfortunately, this means you'd have to go all the way back to step 1 and start analyzing your circuit from scratch. Now students, that brings us to the end of analysis of diode circuits. We are now going to move on to deriving a linear AC model for a diode. So students, in this next part of the lecture, we're going to derive a linear AC model. And looking at the circuit that we have here, we have a DC source and an AC source connected with a diode in series with a resistor. Now it's important to note that this AC source is superimposed onto this DC source, and also that the AC source is much less than the DC. So we call it what is a small signal. Now if we were to visualize or represent this graphically, what is the voltage VD and the current ID through this diode? Looking at the current ID, here we have IDQ represented by the yellow line over here, and that is the DC current that is going through the diode. Now on the other hand, this purple curve, which is a small letter ID, that represents the AC current that is going through our diode. On the other hand of our voltage, VD, VDQ, which is represented by the red line, that is the DC voltage across our diode. And this green curve over here, small vd, that is the AC voltage that we see across our diode. Now if we were to take our voltage and current across our diode and we were to see where it appears on the characteristic curve for our diode, remember the diode is forward biased because our DC source is connected in series with it, or rather the DC source is connected to the anode of our diode. We know that it is going to be forward biased. So when we look at our characteristic curve, we can go to our two Q points, which is our IDQ and our VDQ. That is the DC voltage and the DC current. Students, you should have remembered the Q point from the graphical analysis of diode circuits in the previous lecture. So now we have our Q point represented by our IDQ, our VDQ, which are our DC voltage and current. And then superimposed on this DC voltage and current is we have our AC voltage and current, which is small id. As you can see, it has a positive and a negative. We have our AC voltage, VD, which also has a peak and a trough, and it's here on our characteristic curve. So we're only looking at this section of the characteristic curve, this little segment, which is cut out according to the AC signals that are superimposed onto our DC Q point. And because we are just looking at this little piece of the graph, students, you know that the slope of the graph represents some sort of a resistance. Yes, so the slope of the curve is 1 over small letter RD, which is known as the small signal incremental resistance. And we know that resistance and conductance are related, so small gd, that is our small signal incremental conductance. Now using this characteristic curve and circuit, we're now going to go ahead and actually derive an AC model. So first thing that we need to do is we're going to be looking at the voltage current relationship. Looking at the diode equation, which you should remember, you might think, but sir, what happened to the -1 in the equation? Well, for this derivation, students, the -1 is negligible, so we're going to leave it out. So starting off with the diode equation, we rewrite it by simply expanding on our exponent. And our exponent can be represented by our DC Q voltage and our AC voltage divided by our thermal voltage. So we've simply expanded it, and here we have the DC component because we have our VDQ, and here we have our AC component because we have our small vd, which is our AC signal. Now then, students, please follow with me. If our AC voltage Vd is much less than our thermal voltage Vt, then we can do this expansion of the exponential into a linear series. Now we're going to take you back to your math all the way back here. I don't know if you guys have covered this yet, but I hope you have, or I hope that you will soon. But we're going to expand an exponential into a linear series, and this is a Taylor series, students. So familiarize yourself with the Taylor series, and then what we do is simply e to the x, or exponent to the x, can be approximated by 1 plus x, for our x being approximately 0. And we know that it's approximately or very close to 0 because our AC voltage Vd is much less than our thermal voltage Vt. Remember, looking at this fraction over here, because our numerator is much less than our denominator, then we know that this is a very, very small number, or very close to 0. And that's why we can represent this using the first order polynomial, and we have 1 plus Vd over Vt for this exponent. So that's how we get that. And then we look at the AC component, or rather the DC component of this equation over here. We simply know that our IDQ, which is our DC current, can be represented by that DC component of the equation. So we take this approximation, or rather expansion of a exponential, and we take this DC current and we replace it in the equation ID to end up with this. Now on to the next step, students. The equation that we end up with, ID, is equal to all of this, which eventually leads to our current through our diode is equal to the DC current plus the AC current. Very simple. And how will we arrive at that? Well, students, these are the two main equations for the derivation, where we can represent the AC current ID by the DC current divided by the thermal voltage multiplied by the AC voltage. And that, students, gives us the incremental conductance. This term over here is the incremental conductance multiplied by our AC voltage. Similarly, if we look at our AC voltage, we have our thermal voltage divided by our DC current, IDQ, multiplied by our AC current, and we can replace this part of the equation here by our incremental resistance, RD, and simply multiply that by our AC current. And remember, students, the relationship between conductance and resistance over here, and we have RD is equal to 1 over GD, which is equal to our thermal voltage divided by our DC current. Now let's take that AC model that we derived and put it into action with some circuit analysis. So the circuit and diode parameters for the circuit shown are DC voltage of 8 volts. We have a resistor in series there, which has a resistance of 20 kilo ohms, diode on voltage of 0.7 volts, and we have our AC small signal, which is 0.25 volts peak sine wave. And what we're asked to do is to determine the quiescent diode current IDQ. Very difficult word to pronounce, students, so I'm just going to say Q from now on. So the Q diode current IDQ and the time varying diode current ID, or small id. So we can immediately notice that our DC voltage is 8 volts and our AC voltage has a peak voltage of 0.25. They are much different. The AC voltage is much less than the DC voltage. We know that this is a small signal. So First thing that we do with an analysis like this is we perform a DC analysis followed by an AC analysis. So for the DC analysis, we have to set our AC signal to 0 and draw an equivalent circuit and proceed with an analysis. So here is the equivalent circuit. I've replaced our AC source with 0, a short circuit, and then we're going to just do some good old-fashioned KVL, students. So from our KVL equation, we can get the current or the DC current, and that is simply 0.365 milliamps. And using the current and Ohm's law, we can calculate the output voltage, 7.3 volts. Very simple. Now students, the AC analysis is very similar to the DC analysis in that we have to replace our DC source with a short circuit. So we set it to 0 volts. We're only working with the AC source. And that's what we do here. And recall that our AC source is much less than our DC source, 8 volts versus 0.25. So it's a small signal. Now you're looking at this resistor and wondering, sir, where did that come from? Well, students, because we're working with the small signal at this point in the analysis, we replace our diode with its small signal incremental resistance. You don't have to worry about the constant drop model or the piecewise linear model, because that model would be used for the DC analysis of the circuit, which you would have recalled we did previously. So for the AC part of the circuit analysis, we simply replace our diode with the small signal incremental resistance, RD, and then we do some good old-fashioned KVL. You know it, you love it. So here we arrive at our KVL equation, and from our KVL equation, we are able to calculate our small signal incremental resistance, which is 71.2 ohms. And students, this is the equation that we derived. That one equation that we derived from that entire AC model is this. Here we are using it in this example just to calculate our 71.2 ohms. And once we get our small signal incremental resistance, we can use some good old-fashioned Ohm's law to calculate the current going through our diode. And as you can see, it peaks at 1.25 microamperes. And yes, that is a lot smaller than the DC or IDQ current that we calculated previously. From what I recall, it was about 0.3 milliamps, which is much greater than this. So we are indeed working with a small signal. And that, students, brings us to the end of this lecture. To recap, we went over some diode models where we looked at a diode model for an ideal case, the constant drop case, and the piecewise linear case. We then looked at some diode circuits which only had single diodes in the circuits. Very simple and easy analysis to get you guys kicked off. We then looked at multiple diode circuits, starting off with a series analysis, moving on into a parallel analysis, and finally we looked at some more complex circuits. And if you recall, students, when we were looking at the more complex circuits, there were 4 steps that you had to take when analyzing those circuits. The first being that you have to make an assumption on the state of the diodes in the circuit. The second step being that you had to redraw the circuit based on the assumptions you made. The third step being analyzing the circuit and checking whether your assumption was correct or incorrect. Some very important equations there, students. Don't forget to always have them on hand when doing multiple diode circuit analysis. And then finally, the 4th step was if your assumption was incorrect, oh dear, unfortunately, you'd have to go all the way back to step 1 and restart your analysis with a new assumption. Once we concluded diode circuits and their analysis, we went on to a derivation of a linear AC model. It was an approximation that we used a small signal AC source and it was superimposed onto a DC source. We took a look at what that looked like on the diode characteristic curve for a forward biased diode, and then we performed our AC model analysis. In a circuit analysis, we actually saw this in action and we calculated our small signal incremental resistance and used that to analyze the circuit. Now students, if there was anything you're not clear on in this lecture, please refer to your textbook, the following chapters and pages. And of course, You're more than welcome to come to the lecture enrichment sessions with any questions, comments, feedbacks, criticism. I'd appreciate any of it. Thank you for your time. Goodbye.